When installing a generator in a remote location, several key considerations must be addressed to ensure a safe and efficient electrical distribution system. Firstly, a thorough site assessment is essential. This involves confirming the generator's output and the load requirements of the facilities it will serve. A detailed survey should be conducted to determine the exact distance and location of the generator relative to the load. This information is critical for calculating voltage drop and selecting appropriate wire sizes. Secondly, electrical calculations are paramount. The required wire size for both 240 volts and 480 volt circuits must be calculated, taking into account the load and the significant distance of 1200 feet. It is important to consider voltage drop and power losses in the distribution system, as these factors can significantly impact the performance and efficiency of the electrical supply. Thirdly, the use of step-up and step-down transformers should be carefully evaluated. A 240 volts to 480 volt step-up transformer can substantially reduce the required wire size, especially given the long distance involved. Step-down transformers with integral load centers offer a convenient solution for power distribution. It is imperative to choose transformers that are appropriately rated for the load and fully compatible with the generator's output. Moving on, distribution and branch circuits need careful planning and implementation. 480 volts feeders should be run from the generator to the first step-down transformer. To protect each branch circuit, install circuit breakers or fuses. Proper grounding of the distribution system and all associated equipment is critical for safety. Step-down transformers, in this configuration, do not constitute a separately derived source. The generator and all electrical equipment must be grounded in strict accordance with local codes and regulations. Ground rods or other suitable grounding methods should be considered to ensure a robust and reliable grounding system. Safety considerations are of utmost importance. Ensure that all electrical components are properly installed and meticulously maintained. Employ weather-resistant materials and adhere to proper wiring practices to protect the system from environmental factors. Comprehensive safety training must be provided for all personnel responsible for operating and maintaining the system to prevent accidents and ensure safe operation. To further enhance understanding and ensure compliance, several additional resources can be consulted. Firstly, review resources on electrical distribution for remote communities, which provide valuable insights and best practices. Secondly, adhere to National Fire Protection Association 70, the National Electrical Code, which sets the standard for safe electrical installations. Thirdly, consider IEE 141.1993, the IEE recommended practice for electric power distribution for industrial plants, which offers detailed guidance on power distribution systems. Extending the 480 volts distribution from the first distribution point to a second step-down transformer requires careful planning to maintain safety and efficiency. To extend the 480 volts supply, run appropriately sized conductors from the load side of the first step-down transformers disconnect to the input terminals of the second step-down transformer. The wire size must be calculated based on the load demand of the second transformer and the distance between the two transformers to minimize voltage drop. Use conduit or cable trays for physical protection and secure mounting of the conductors. Install a disconnect switch or circuit breaker at both the supply and load ends of the 480 volts feeder. This allows for safe isolation of the circuit during maintenance or in case of a fault. Ensure that all components are rated for 480 volts and comply with local electrical codes. For example, use THHN or XHHW wires in conduit for durability and safety. Grounding is a critical aspect of extending the 480 volts distribution. The neutral conductor is bonded to ground at the generator. At each step-down transformer, the neutral conductor is also bonded to ground. This creates a multi-grounded neutral system, which helps to ensure safety and reduce the risk of electric shock. The ground wire should be connected to a grounding electrode system, such as ground rods or a buried ground ring. The size of the grounding conductor must be in accordance with electrical codes and should be adequate for the fault current that may occur. Remember that step-down transformers in this configuration do not constitute a separately derived source. The neutral conductor is bonded to ground at the generator, so additional ground rods are not required at each transformer. Instead, focus on ensuring a continuous, low-impedance ground path throughout the system. When planning the layout of the electrical distribution system, consider the physical environment and potential hazards. Avoid running conductors through trees or areas where they could be damaged by vehicles or equipment. Use appropriate enclosures and fittings to protect the conductors from moisture, dust, and physical damage. Provide adequate clearances around electrical equipment for maintenance and ventilation. Ensure that the transformers are installed in well-ventilated areas to prevent overheating. Consider using surge protection devices at the generator and at each step-down transformer to protect against voltage spikes and transients. These devices can help to extend the life of the electrical equipment and reduce the risk of damage from lightning or other electrical disturbances. Additionally, ensure that all electrical panels and equipment are clearly labeled with voltage, amperage, and other relevant information. This will help to prevent confusion and ensure that personnel can safely operate and maintain the system. Provide clear instructions and training to local personnel on the proper operation and maintenance of the electrical distribution system. This should include information on how to safely switch the generator on and off, how to check for faults, and how to perform basic maintenance tasks. Emphasize the importance of using qualified electricians for any major repairs or modifications to the system. Consider implementing a preventative maintenance program to ensure that the electrical distribution system remains in good working order. This should include regular inspections, testing of protective devices, and cleaning of equipment. Keep detailed records of all maintenance activities and any repairs that are performed. This information can be helpful for troubleshooting problems and planning future maintenance. Remember to consult with a qualified electrical engineer or contractor to design and install the electrical distribution system safely and efficiently. Their expertise is invaluable in ensuring that the system meets all applicable codes and standards and that it is appropriate for the specific needs of the remote village. Consider their input on wire size, transformer selection, grounding requirements, and overall system layout. They can also provide guidance on the selection of appropriate protective devices and surge protection measures. They can also help to identify potential hazards and recommend appropriate safety measures. The engineer or contractor should be familiar with the electrical codes and standards that are applicable in the Congo. They should also have experience working with remote power systems and be able to provide practical solutions for the challenges of installing and maintaining such systems. They should also be able to provide training to local personnel on the proper operation and maintenance of the system. It is essential to prioritize safety in all aspects of the electrical distribution system. The lives of the people in the remote village depend on it. Ensure that all electrical work is performed by qualified electricians and that all applicable codes and standards are followed. Provide clear instructions and training to local personnel on the safe operation and maintenance of the system. Regularly inspect and maintain the system to prevent problems and ensure that it continues to operate safely. By taking these precautions, you can help to provide a reliable and safe source of electricity for the remote village. The system must also comply with local electrical codes and regulations. These codes are designed to protect people and property from electrical hazards. It is important to consult with a qualified electrical engineer or contractor who is familiar with the local codes and regulations. They can help to ensure that the system is installed in accordance with these codes and that it is safe to operate. The system should also be designed to be as efficient as possible. This will help to minimize the amount of fuel that is needed to run the generator and will reduce the cost of electricity. There are a number of ways to improve the efficiency of the system, such as using energy-efficient appliances and lighting, and by minimizing the length of the electrical circuits. The system should also be designed to be as reliable as possible. This will help to ensure that the village has a consistent source of electricity. There are a number of ways to improve the reliability of the system, such as using high-quality components and by providing backup power sources. Finally, remember that it is often best to provide local villagers with training to maintain their systems themselves so that they do not have to depend on outside technicians. This will help to ensure that the system is well maintained and that it will last for many years to come. Consider the following additional advice. Grounding systems are crucial for electrical safety, especially in remote installations. A proper grounding system protects against electrical shocks and equipment damage. In your scenario, you're dealing with a generator supplying power over a significant distance. The grounding requirements vary based on whether the system is considered a separately derived system or not. Separately derived system. A separately derived system is a power source, such as a generator or transformer, where the neutral is isolated from the supply source. In such systems, the National Electrical Code (NEC) requires specific grounding measures. This typically involves installing a grounding electrode system, such as ground rods, and bonding the generator or transformer neutral to this grounding electrode system. Not a separately derived system in your case, the step-down transformers do not constitute a separately derived source because the neutral is already bonded to ground at the generator. Therefore, you do not need additional ground rods at each transformer. Instead, focus on maintaining a continuous, low-impedance ground path throughout the system. This is achieved by ensuring that all metallic enclosures, conduits, and equipment are properly bonded together and connected back to the main grounding electrode system at the generator. Grounding best practices connect all metallic enclosures, conduits, and junction boxes using appropriately sized grounding conductors. Use grounding bushings and bonding jumpers to ensure continuity around knockouts and conduit joints. Run a dedicated equipment grounding conductor with the circuit conductors to provide a low impedance path for fault currents. Size the grounding conductors according to the NEC tables based on the size of the ungrounded conductors. Test the grounding system to ensure that it has a low impedance path to ground. This can be done using a ground impedance tester. Safety recommendations. Electrical safety is paramount. Given the existing hazardous conditions you described, lamp cords strung through trees and bare wires, it's critical to implement safe practices. Use appropriately rated and insulated conductors for all wiring. Ensure that all connections are secure and protected from the environment. Install ground fault circuit interrupters (GFCI) for all 120-volt circuits, especially in damp or outdoor locations. Provide clear warning signs and barriers to prevent unauthorized access to electrical equipment. Conduct regular inspections and maintenance to identify and correct any potential hazards. Engage qualified professionals. Given the complexities and risks involved, it's highly recommended to consult with a qualified electrical engineer or contractor who has experience with remote installations and can ensure compliance with local codes and regulations. They can perform detailed calculations, select appropriate equipment, and oversee the installation process to ensure that the system is safe and reliable. In summary, when extending the 480 volts distribution, focus on using appropriately sized conductors, providing physical protection, installing disconnects at both ends, and maintaining a continuous, low-impedance ground path. Consult with a qualified electrical engineer or contractor to ensure that the system is designed and installed safely and in compliance with all applicable codes and regulations. Remember, the safety of the community depends on the proper installation and maintenance of the electrical system.